lesson is about linearizing graphs. This is from the AP workbook. It's L. And this is a technique that you're going to need to know because sometimes graphs are not linear. When they aren't linear and you are in the middle of a test, you don't have access to Excel, then how do you generate the equation of the line? How do you generate use the area when there's a curve? And so linearization will assist you in determining values and relationships when you don't have access to those things, okay? So that's what we're going to practice. Angela, Blake, and Carlos have been given a stopwatch, several large spheres, and a meter stick, and have been asked to determine acceleration due to gravity. They decide that they need to collect drop height and time to fall for the ball at several different heights to create a position versus time graph, and here's their data. First, we're going to graph their data. So we've got 0, 0. We've got a height of 0.5, happens at 0.32. We've got at 0.4 seconds, 0.75, 0.46, and 1, and 1.25, and 0.5. So this, I didn't do this very well because my printing isn't coming out very good, as we get a curve like that. Based on your graph and the table at the right, identify the correct relationship. So this, right, you should know this. My printout again didn't come out fantastic, so let me just fill this in. If they're increasing, if it's directly proportional, it's going to be linear. Let me get a different color. It's going to be linear. Inversely proportional, looks like that. Proportional to the square and the square of y. Oops, wrong way. Sorry, not that. That. Okay, so that's what that looks like. So which one matches what we have here? Well, it's definitely the proportional to square. So the drop height is proportional to the square of time. So the relationship between drop height and time to fall can be compared to the equation for a line so that the students can create what's called a linearized graph. Fill in the third column of the data table with appropriate values. So what we're looking at, and what this says is height is proportional to t squared. That's what we're seeing here. And so if I want to make a linear graph, then I need this on the y-axis and I need this on the x-axis. So I need another column because I need time squared. So that's what I'm going to fill in this column. I'm going to go, well, 0 squared is 0, 0.32 squared. I'm just going to calculate this. Now, when we do this in the lab, you're just going to be able to use Excel, which makes it a heck of a lot easier than typing it in each time, but that's fine. 0.2116 and 0.5 squared is 0.25. So now we've got this data, and on the back, we're going to then it says, what quantity should be plotted on the graph if the graph is to have a linear trend and the slope? So we're going to put height on the y-axis. We're going to put time squared on the x-axis. Now, what does that have to do with acceleration due to gravity? Well, if we have our equations, right, if we're going to say h is proportional to t squared, right, we're looking for a linear graph, then we're going to have y equals mx plus b. Well, what equation do we have that looks like that, right? What equation do we know of that takes these two and makes them proportional to each other? Hopefully you recall our kinematics equation that says displacement is VOT plus 1/2 AT squared. And rearranged, right, I'm just going to take this and I'm going to rearrange it, where delta D equals 1/2 AT squared plus VOT. And what that's going to do is it's going to tell you that the distance, right, is your height, the time squared is on the x. The slope is going to be 1/2 a, and your y-intercept is going to be VO times t, which is kind of interesting, right? So that's how we're going to figure this out. All right, this is what we're going to look at. So when we make this graph, I gotta keep flipping back and forth to get my data. So my first point is still 0, 0. My next point's gonna be 0.5 and 0.1. My next point's gonna be 0.16 and 0.75. 1.0 and 0.21. And last, 0.25 goes with 1.25. So now this roughly makes a straight line. So when I do this, I want to make sure I make it a nice balanced line. Okay, and there's my best fit. So now I can find acceleration due to gravity. We already said the slope, right, of this h versus t squared is going to be 1/2 a. Here's my proof right there. This is using the mathematical model. Okay, so then so if I find the slope, which is going to be delta y over delta x. So you can pick any points on this line, but don't use your data points unless they are actually on the line. None of my points are on the line except for 0, 0. And yeah, this was a little crooked. Except for 0, 0, so I can use that. And then I'm going to pick one other point. Let's see if I have a nice one along my line. Looks like, well, right here. Right, this is the point I'm going to use for my slope. So my y is 1.05 and my x is 0.22. So you can use any points that are already on your line, and that's going to equal 1/2 acceleration. So 1.05 divided by 0.22 is 4.77. is equals 1/2 a, so if I multiply that by 2, I get 9.55 is my acceleration due to gravity. Now, obviously, that's not acceleration due to gravity. Acceleration due to gravity is supposed to be 9.8. So, but that's pretty darn close. So you might have a slightly different value because you might have drawn your points a little differently. You would draw your best fit line a little bit differently, right? Maybe I should have obviously shifted it up a little bit because this is a little bit too small. But that's acceptable as long as you show your work.